In this video I will introduce the JTAG interface, an interface that you can find on almost all of your IoT devices like routers, webcams, electronic toys, TV remotes and so on. I will explain why this interface can be so useful in hardware hacking and how to find its position and pinout using simple techniques and tools like, for example, using a multimeter or a cheap Jtagulator board. And when the pinout is known but the JTAG interface is not working, I will explain the reasons why this can happen and what to do to solve this issue. I am Valerio Di Giampietro. I am an electronic engineer with a background in digital electronics and information technology infrastructures, and I would like to be your friendly Italian hacker neighbor willing to share with you tools and techniques for hardware hacking that I learned by myself hacking many devices. And now, let's start! This is the third episode of the series Hardware Hacking Tutorial. In this complete series, we will talk about the hacking process based on information gathering from our device, building an emulation environment where to run interesting binaries, discovering how the device works, and at the end, hack the device and modify its firmware. In this episode, we will talk about how to find the JTAG interface and why this interface is so important in the hardware hacking process. The JTAG interface is an industry standard usually implemented in complex integrated circuits. This standard was issued for the first time in 1990 with the purpose to simplify the testing of PCB after manufacture. It allowed controllability and observability of each bit of internal memory of each integrated circuit and allowed to check the integrity of each single trace connecting different integrated circuits in the printed circuit board. Controllability is the ability to easily set to 0 or to 1 each internal bit of memory of an integrated circuit, to verify that none of them is stuck at 0 or 1. Observability is the ability to check the value of each internal bit of memory register, and it is achieved using additional circuitry and specialized long shift register. A side effect of this purpose is the possibility to read and write the flash memory content, and with later improvement to the standard, the possibility to use the JTAG interface as the primary means to do in-circuit debugging. That means being able to run a debugger on the real firmware running on the real hardware. Multiple integrated circuits in a printed circuit board are daisy-chained together so that we can access each one of them. The JTAG interface usually has 4 or 5 pins, because one is optional. The pins are the test clock, test data in, test data out, test mode select and test reset. Test reset is optional because it is possible to reset the interface with a command sent using the other pins. In hardware hacking project, we are very interested in the JTAG interface, mainly for 2 reasons. The first reason is that it allows us to read and write the content of the EPROM, so it can be used to dump the entire EPROM content. It can also be used to restore the original firmware in case of breaking the device during our firmware modification trials. Obviously, we should have saved the original firmware before tinkering with it, but every one of us do this. It also allows to break into the boot cycle and allows us to use the JTAG interface as a means to do in-circuit debugging. This means using a debugger, like for example the GNU debugger, with the real firmware over the real hardware. Doing this kind of things is not easy because there is a lot of information on internet on how to proceed, but it is quite complicated. And we also need a serial-based interface board to attach a PC to the JTAG interface. The two most popular interface boards in the open source and hacker community are Bus Pirate and Bus Blaster. There are also some other interface boards. Anyway, you will find the links in the description below. We also need the software to interact with the interface boards and the JTAG itself, to dump the EEPROM content or to enable in-circuit debugging. The most popular software in the open source world is OpenOCD. You will find the link in the description below. To find the position of the JTAG interface, we follow the easiest path first principle. This means that first of all we search on internet to see if someone else has already done the job for us and has already found where is located the JTAG interface in our device. For our sample LinkM Gemtech router that we have already used in the previous episode, there is no information on internet about this interface, so we have to find it by ourselves. We can start looking at the board, searching for pins labeled with the names of the JTAG interface like TCK, TDI, TDO and TMS. But in our sample router board, we weren't able to find this label. But in few boards, like for example the one shown here, we are able to find these labels, and so the job is quite easy. But if we are not lucky in searching on internet and in looking at the labels on our board, finding the position of the JTAG interface, it's not easy. One of the reasons is that there are no standardized connectors and pinout. Anyway, there are few popular pinouts. Some of these pinouts are available on the JTAG test websites, link below in the description. This website seems not to have been updated recently, but probably it still has the largest number of popular JTAG connectors and pinouts. The most common pinout are logically arranged based on the system on a chip that you have on your board. Often, for the same system on a chip, you can have many possible pinouts. Sometimes it's the system on a chip manufacturer to recommend a specific pinout. Sometimes it is the board manufacturer that prefer a specific pinout, and some other times the pinout is totally custom and it is not available on this website. Anyway, this website is a good starting point. If we don't find any JTAG pin label on our board, we start searching for pin headers arranged in a single row of 5 or 6 pins or in a double row of 10, 12, 14 or 20 pins. When we have found the pin candidates, we can use a multimeter to find the possible pinout, because finding ground and VCC is easy. Usually TMS and TDI have a pull-up resistor. Test reset usually have a pull-up or can also have a pull-down resistor, and TDO should be an high impedance input. Once we have identified with the multimeter ground and VCC and taken pin resistance and voltage measurements, we can compare what we have found with the popular pinout in the JTAG test website, and if we are lucky, we can identify the JTAG pinout using only a simple multimeter. We will see later a demo of this approach. If we know the system on a chip and if we have its datasheet, we can locate the JTAG pins on the chip and then follow PCB traces to identify the connector. But this is usually very difficult for at least two possible reasons. One is that often the system on a chip is a surface mount device with the pins below the package, and it is impossible to identify them on the printed circuit board. This is, for example, the case in our sample Gemtech router. When the system on a chip has a package that shows its pin, like in this case, the case is shown, and it is easy in this way to identify the JTAG pins, it can be difficult to follow the traces on a multi-layer board, and today almost all boards are multi-layer. The best and easy solution, once we have identified potential JTAG pin candidates is to use Jtagulator. Jtagulator is a fantastic tool. It has a lot of headers that we can attach to potential JTAG pin candidates, and then it can run some automatic scanning logic and can identify the JTAG pinout. Later we will see how to use Jtagulator. We can try to find pin headers candidate on our sample Gemtech router, but as you can see, we don't have anything that is similar to a single row of 5 or 6 pins or a double row of 10, 12, 14 or 20 pins. If we look carefully, we can see that we have a lot of small pads labeled TP1, TP2 and so on. The TP in the label probably means test point, and probably these test points are used to test the printed circuit board after manufacture using a bed of nail tester, as the one shown here, where the board is pushed down toward the bed of nails and some automatic test is executed. Probably in our sample board the JTAG interface is available on some of these test points, but these pads are very small. I have not available any bed of nail tester, and I am not so good at soldering wires on these so small pads. This means that I am not able to find the JTAG interface on this board. Following the easiest path first principle, I anyway move forward in the hacking process of this board, and I will return back to find another way to connect to these test points only if absolutely needed, and only if I will not be able to get the firmware out of the EEPROM in some other way. To show how to find the JTAG pinout using a multimeter, we use another router's board that I have hacked in the past. In this case, it is an old Huawei router, an HG553 distributed in Italy by Vodafone. If we look at the board, we can see that the system on a chip is a Broadcom MIPS chip, and that the possible header candidates are in the other side of the board and are these pads, 10 pins arranged in a double row. With the board powered off, we can start taking resistance measurements against ground, and we start with pin 1, then pin 2, and so on, up to pin 10. We annotate these measurements on a notebook. Then we start taking resistance measurements against VCC. We can get a VCC reference from an integrated circuit on the board and this datasheet. We start with pin 1, then pin 2, and so on up to pin 10, and we annotate these measurements on the same notebook. Then we power up the board, switch the multimeter to voltage measurements and start measuring voltages on each pin, starting with pin 1 and ending at pin 10, and we annotate these measurements on our notebook. Based on these measurements, only the position on VCC and ground on this connector is a useful and reliable info, so we can say that pin 2 and pin 10 should be ground because they have zero resistance against the ground, and the voltage measurements when the board is powered on is at 0. Pin 4 should be VCC because it has zero resistance against VCC and the pin is at VCC with the voltage measurements. Pin 6 and pin 8 could be not connected, but we are not sure. Pin 3 seems floating at some random voltage. Could be a high impedance pin, but again we are not sure. Because TDO often is an high impedance pin, this could be TDO. Now we will use this information to search on the JTAG test website and try to search a JTAG connector with 10 pins and with VCC and ground on same position as in our device. We know that our system on a chip is based on a MIPS architecture, so we look at MIPS a JTAG pinout, but this pinout has 14 pins, so we move forward and look at the Toshiba MIPS pinout, but again, in this case the pinout has 20 pins, so we look at the Philips MIPS pinout, but again we have 20 pins. Instead, in our board we have 10 pins. So we try some 10 pins connector like the Cypress Ultra ISR, but it doesn't have a pinout compatible with our ground and VCC position. At the end we find the Altera Byte Blaster pinout that is compatible with what we have found till now. Same position for ground and VCC, 2 not connected pins on compatible position, TDO pin on what we think is an high impedance pin, so probably we have found the correct pinout using only a multimeter. Another possibility to more easily identify the JTAG interface pinout is to use the Jtagulator board. Jtagulator is an open source hardware tool that can be used to automatically identify the pinout of the JTAG interface. It has 24 programmable I/O pins that can be attached to JTAG pin candidates, and it will run some automatic scanning logic to identify the pinout of the interface. Obviously, the interface pin must be included in the pin candidates attached to the Jtagulator board. This board will be attached to a PC using the USB interface. It will be powered by this interface and will be controlled through a serial terminal emulator like PuTTY. We can find this board from various sources, like for example from Adafruits for about $175. In other places maybe you are able to find at lower prices. Being open source, everybody can access his schematics, PCB drawings and bill of materials and build the device by himself. You will find the links below in the description. First of all, we connect the Jtagulator board to a PC using the USB interface. This powers up the board. On the previous episode of this series, I gave some more detailed information on how to access the serial device on our Linux box. So if something is not clear, please take a look at the previous episode, link on the description below. We have to use a terminal emulator like PuTTY to talk to the Jtagulator board. In our Linux system, the serial device is TTY USB 0 and the speed is 150,200 bits per second. Once connected, we press Enter to be greeted by the Jtagulator. Then we type H for help to print available commands, and we can see that we have 3 types of commands. General commands to set the target system voltage, to read all channels as input or to write to all channels as output. Then we have commands to identify the UART pinout or talk directly to the UART from our terminal emulator. We have seen this part in the previous episode. And then we have the commands to identify the JTAG interface pinout. Now we can connect the Jtagulator board to our router board. First of all, we power up the router. And as you can see, I didn't have a proper socket to solder on these pads for SMD devices, so I soldered these pass-through-all connectors, I would say in an improper way, but anyway they are functioning as expected. First of all, we connect the Jtagulator ground to the router board ground. We know that the ground is available on this connector at pin 10, so we connect ground to this pin 10. Then we connect the Jtagulator channel 1 to the router's connector pin 1, then the Jtagulator channel 2 to the router's connector pin 2, and so on, up to channel 9 to the router's connector 9. Remember that we use the pin 10 as ground connection, so we don't need to connect the channel 10. Now we return back to our terminal emulator. We press V to set up the target voltage at 3.3 volt. This must be done before any other command. Then again we press H to list available commands. and we press J to enter the JTAG submenu, then H again to list the available JTAG subcommands, we have two options to identify the pinout. The first option is the ID code scan. It is faster, but doesn't identify the TDI pin. The second option is the bypass scan. It is slower, but will identify all pins, so we'll press B for bypass scan. If we have many pin candidates, it could be better to use first the ID code scan and then the bypass scan to identify only the remaining TDI pin. With the first pass, we'll identify every pin excluding TDI, and with the bypass scan we can identify only the TDI pin. In this case, the entire process is faster. As starting channel, we select 1 because our channel 1 is connected to the first pin, the pin 1 of our connector. As ending channel, we select 9 because the pin 9 is connected to our pin 9 of our connector. Remember that pin 10 is connected to ground, so we have only to connect channel 1 to channel 9. We don't have any pin already known, so we accept the default no answer. Jtagulator informs us that it will try 3024 combinations. We accept the default to not bring low each channel between permutations, then we press the space bar to start scanning. After few minutes, Jtagulator gives us the pinout that it has found. We can see that this confirms what we already found on the previous step. TDI is at pin 9, TDO at pin 3, TCK at pin 1, TMS at pin 5, and test reset at pin 8. This optional pin was not listed on the JTAG pinout website. Now that we have identified the JTAG connector, we have the possibility to attach to it an interface board like Bus Blaster or Bus Pirate or some other boards. You will find the links below. Then we can use OpenOCD for reading or writing the EEPROM content and start using a debugger like GDB, the GNU debugger, to do in-circuit debugging on the real firmware, on the real hardware. But doing this kind of thing is not easy. I will show you some example in some future episodes on this channel. Before ending this episode, a very important warning I have to tell you about finding the JTAG pinout. Because also if you find the JTAG connector, visually inspecting the board, checking with the multimeter, and comparing what you have found with the JTAG test website, more often than not, you will not be able to confirm the pinout with the Jtagulator, and you will not be able to use OpenOCD or other software to interface to your JTAG connector, because there are many possibilities that this interface has been disabled. Maybe in the mass production it is missing the pull-up resistor and the test reset pin. In this way the JTAG interface is always in a reset state and it will not function. This issue can be solved putting a resistor of about 300 ohm or 1 kilo ohm between this pin and VCC. Usually between each JTAG connector pin and the related system-on-a-chip pin there is a low-value resistor that can be missing during mass production and can be included only in the prototype boards. This issue can be solved putting back the resistor or making a direct connection, short-circuiting the resistor pads. In this case, we'll eliminate a small protection against the system-on-a-chip pins, but it will function. Many system-on-a-chip have multiple functions assigned to the same pin. Writing to a CPU register, it is possible to select what kind of function you want on a certain pin. For example, in the ESP32 Vroom 32 datasheet, we can see that the JTAG pin TDI can be only one of many possible functions available on pin IO12. Same thing for JTAG pin TMS and IO14, and so on. Often, after boot in our device, the JTAG pin is not available because another function has been selected on the multifunction as system-on-a-chip pin. Many system-on-a-chip also have the possibility to temporarily disable the JTAG interface, and this can be disabled writing to a register, and usually do this operation the bootloader or the operating system. Few system-on-a-chip can permanently disable the JTAG interface with an instruction blowing a fuse. In this case, there is no possibility to bring back the JTAG interface unless you have expensive specialized equipment and you are a silicon expert. If the JTAG interface has not been permanently disabled, usually it will be available when our IoT device cannot boot. Maybe it is a corrupted bootloader. In these cases, no instruction has been executed yet on the system-on-a-chip to disable the JTAG pins, and they are available to be used to restore the content of the EEPROM and to unbrick the device. For this reason, in many devices we can find documentation internet on their JTAG interface. We can use their JTAG interface to unbrick the device, but when the device is normally functioning, the JTAG interface is not available. If you have found this video interesting, please subscribe, help this channel grow, share this video with friends interested in hardware hacking. Please click the subscribe button below and the notification bell to be notified when new episodes will be released. And don't forget to click the thumbs up icon. Please let me know in the comment below if you have tried to use the JTAG interface, on what devices you have tried, the problems you have faced, and if you have been successful or not in using the JTAG interface. Please give me feedback, writing comments below. Let me know if you have suggestions to improve this channel, if you enjoyed this video or if you didn't like it, or if you have any other type of comment. Every comment, but positive and negative, is welcome. Thank you for watching. See you again on this channel.